We are. Let's go ahead. So, first question. Afnan, are you here? Take the first question. Where's he? No, he's not here. I think he might join back again. Who want to take this question? Can someone read it? Mahi, read it. Hello.
Yeah. Let
Just read the
G
question.
be a complete undirected graph on 4 vertices having 6 edges with weights being 1, 2, 3, 4, 5, and 6. The maximum possible weight that a minimum weight spanning tree of G can have is.
Hmm.
Okay.
Okay. So, what do we understand from this? Wait, what should I do? Can you help me do this? Wait, let me just open Paint. It's here. Fine. So, complete undirected graph. What is a complete graph? Can someone tell about that? Having 4 vertices. Okay. So that's all. A complete graph is like a fully connected graph, right? So since we have just like 4 edges, 4 vertices, Mahi, able to follow?
Yeah.
Okay. So fully connected graph will look like this. So there are six edges, am I right?
Yeah.
And they are saying like weighters like 1, 2. We can give anything. I think 3, 4. Let's say this is 5 and 6. Okay. So maximum possible weight that a minimum spanning tree can get. Okay. What does this look like? I mean, so what is being asked here? I think
MST
they're
is
just
what?
asking for minimum cost connectivity, right? Uma, you want to say something?
No, we asked for MST, right? Minimum spanning tree, that's all.
Okay. How do we do that?
We choose either by Kruskal or by premise.
Okay. I'm just taking 1 to 2, right? So 2 to 3 it is 2, and then using this and 3. So what does this look come like? So this is summing up to a total of what? 6, right?
6.
So this is the minimum possible weight for MCST,
Oh,
right?
maximum possible weight. Okay. So we have to choose the maximum weight and this several.
Maximum
How do we do this question here?
1, 2, 3, 6.
Instead of 1, we can try 1 to 3, 1 to 2 instead of 1 to 2.
1, 2, 3.
Excuse me. Tell me. Repeat. 1, 2.
3.
Okay. 1, 2, 3. But see, I think this question is based on the arrangement of the edges here. Okay. If you draw the edges like this, come on. If you draw the edges like this, 1, 2, 3, 4, 5, 6. If you're drawing it like this, then you will get the MCST as 6. Okay.
Yeah.
But if you draw it like, I'm just gonna do it again. 4. I remember doing this question. That's why. Okay. So now let's give. So 5 and 6 were in the this thing, right? So I'll try to give it there outside somewhere. I'm not sure. Okay. 1, 2, this is 3, and this is 4. Okay. So in this case, what will be the MCST?
It'll
1,
still be 1, 2, 3.
2. This is 3. Have we connected all? Oh. So there should be a way like 1, 2, 4 will be coming up.
Yeah, if you exchange the 3 and the 6 edge, right? Okay, that
Okay.
also won't.
Mm-hmm. 1, 2. It was 3 and 4. I think I delete. So, what if I took? Okay. So I'll do something like this. Wait. I'm gonna
This
put.
question is not mentioned anything, no? So everyone can have their own arrangement of weights, the answer will differ, right? Will it not differ?
No, so they're telling us to find out what is okay. So given all the minimum cost spanning trees, what is the maximum possible weight of that entire graph, right?
Hmm.
So you can create how many? So if you have these many edges, right? You six edges. You can
Mhm.
create multiple, uh,
Combinations of.
you can assign weights. Yeah, you can have different combinations. So you should try to find out the one which has the maximum weight.
Okay.
Yeah. So 1, 2, 3 in a cycle will help you remove the 3 and get a 4, right? That's what he did now. So in this case, if you do 1 and 2, 3 you cannot add because it creates a cycle. I mean, yeah. So you have to add 4.
What if I
Four
put
will
four
four will
here,
go like yeah.
4 here, and then
3.
Yeah, between 2 and 4 have 3. Yeah.
between what? Repeat. Two.
Yeah, it's right. It's right. This is right. So between 2 and 4, you have a 3. So once you use 1 and 2 to connect, sorry, edge weight with 1 and 2, right? 1 comma 4, if you connect,
Mm-hmm. Then I can
and
connect one
1
and two,
comma
and
2 you
one and
connect.
three also I can connect with the same, right? So it will still be a minimum cost spanning tree with
No, no,
one,
no.
two.
2
What?
comma 4 has the weight 3.
Sorry. Ah, okay, okay. Wait.
Yeah.
Let me write it properly.
Just that the third edge should form a cycle. So that in that
Correct,
case, you
correct.
won't be able to. Yeah.
So three here and four here.
Yeah.
That's
Yeah.
exactly that's correct. Hmm. So Uma, now you try to like no Mahi. Now you try to draw the MCST here.
Maximum
Yeah. No. For this graph, I'm asking you to draw MCST for this graph.
when for two.
1 to 4 it is 1, right? You start
Yeah,
with the minimum, right?
yeah, and then two. It's two,
Mm-hmm.
and then three.
You can't draw tree, right? Like if you're drawing tree, then it will be a cycle. Get my point. See, if you're doing like this, it's a cycle. So three is for this line. Got the point?
No, it's 3.5. How
Three is
can
this.
I say 3 node 5
Okay.
edge?
2 and 5. Are you saying like that?
Yeah, yeah,
Yeah, instead, you can do 1 and 3, right? I mean, you have the minimum cost here. Get my point? Like, see, so 1, 2, and how do you do that? Okay, start with the
yeah.
edge
Oh
to
yeah,
the right point.
yeah. Okay, 1 to 3. Yeah,
3 is not possible, so we go to 4, right? Mahi, you understand?
yeah.
3 is not possible, so you go to 4, and for 4, you are drawing the thing. All right. So now this sum up to what is the sum? It is 7. Got it? So hence the answer is 7. Uma, tricky question, right? First question itself is tricky.
Yeah, but because so we have to try keep on put different even we can get more choices also, right?
Yeah. I mean,
I mean, I
this is
don't
a
think they'll
matter.
ask anything more than this. What they're trying to test you is, um, so you have to have the first two minimum, right? That's always going to happen. Only at the third edge that you add, if there is a cycle, you will
Ignore that.
ignore that, right? And when you ignore that, you get something bigger than that because the next edge is going to be a little bigger, right? Or else you would have chosen that edge, right?
But in the exam we have to like we won't click it, right? So we have to write it all the possible ways of spreading the
It's
weights and then
impossible to write all the possible ways.
Exactly. It's not. See, that's what I'm saying. So what you should do is that the first minimum two will always happen. So the minimum two will always join three vertices, right?
yeah.
When you're adding the third vertex, right, third edge, right, and you want to connect it to the fourth vertex, you just have to think that okay, the only way I skip an edge and make the weight increase is by having the third edge as a cycle.
Okay.
And you can even extend this to bigger graph actually. If you think about it, if you have more vertices, you try to skip bigger ones every time. So at the fourth edge you might connect the fourth edge, but after the fourth edge there'll be another there. You can form two cycles, right? So you can form more cycles. I think you can form many more cycles if you have four edges connected already. but they wouldn't like expand this sum. I
Yeah,
think
they
the
would expand this. Yeah, that's right.
yeah because this is the easier one to visualize, or else this becomes too tough for anyone.
Yep.
Yeah.
Even for
Yeah.
them. So don't need to worry. All right.
Mhm.
Uma,
Uh,
so you understand? Yeah. Tell me,
Yeah,
Mahi.
sure.
yeah. So why our 6 is wrong? Like when we did it like this.
So 6 is going to be like so they're asking for the maximum possible weight. So the trick here is how you arrange the edges here. That's the trick. Okay. How are you going to give the weight for the edges? Mahi? If you
Yeah.
give the weights like this, 1, 2, 3, 4, 5, 6, if you're giving the weights like this, so you end up as 6. Okay. If the weight is coming like this, so you end up with 7 as MCST. That is the only point here. Because you
Okay,
still getting
I
it,
would
you're
I
not.
would suggest, if you want to approach the sum, don't start with any edge. Okay, just have the four vertices,
Huh.
right? And try to connect the vertices by one of the edges, right? Have first four vertices, right? And now you know there has to be a edge and one, and you know that you have to pick one because one will always be in your minimum cost spanning tree. So that is going to happen. You can
Hmm.
have the second one as 2. Now you know you want to skip 3, right? There is a possibility for you to skip 3 by making it a cycle. So connect the two edges which have already been connect the two vertices which have already been connected and put that as 3, right? So you wouldn't add that edge, and then you can see that the next edge which you add will be a 4. So don't uh, take different possibilities, but build from a empty graph. You could just put a between 4 and 2, just put the 3, right, if possible.
Um, hmm.
Yeah.
Mahi, what's it out? Mahi, tell me.
Like I am not getting it.
See,
We are getting 7.
how we are getting it 7, right? So if I put 3
Yeah.
here, you will connect it, right? So this will be the MCST. Yes or no?
Yeah.
Mahi?
Yeah.
Okay. So if I put 3 over here, this will be the MCST.
Yeah.
So if I put 3 here, this will be the MCST still, right?
Yeah.
With equal to 6. Okay. So but if I put 3 in this way, it is not going to be the MCST.
Yeah.
Okay. So if I put 3 there, okay, now consider the 3 is over here. And if I put 4 here, so 2, I mean, like MCST is going to be 1 to 4, correct?
Yeah.
Okay, so if I'm not putting 4 over there, if I put 4 over here, tell me, now 3 is connected via 2, right? So this this shape will be the MCST, correct?
Yes.
Mm-hmm. So if I put 4 over here, still the same, right?
Yeah.
So, but I mean, either way, if I have 5 also, like we'll still choose this option, right?
Okay. Okay. Yes. 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 Now I
Little bit.
got.
Okay.
Yeah.
Is it clear for all? We should move to the next question now. Okay, fine. Okay, last question was done by. Okay, Nomit, are you here? Don't worry.
Yes.
We'll also take the answers. Okay, and go ahead now. Come on, read the question.
If we perform the following operations in the given order on the min heap,
Mm-hmm.
then the resulting min heap would be.
Okay, so they say that there's a min heap, and we perform this operations, right?
Hmm.
So first we should draw the min heap here, right?
Yes.
2, 6. They are already told that this is a min heap, so it should be okay. So can you just tell me the numbers? 15 and 20. Is that it? Am I right?
Yeah.
7 numbers. Good. So is this a min heap?
25, 18 is also there.
Oh, sorry, I did not see that. Okay. So 25 and 18. So thank you, Oma. So is this a min heap?
Yes.
How do you say that?
The parent node is smaller than the children.
Very good. All the parent node are smaller than the children node. Okay. So then you are removing the minimum element, deleting the min. How do you delete the min? So you can't directly do that, right? So basically, you take 18 from here, right, and put it over here, right? So basically, you replace 18 to 2 and 2 to here, right? Then you pop 2 from here, right? That is how it is going to happen, right? Uma?
No, from the root only we pop, no? Do we?
Yeah. No. We don't directly pop from the root.
Okay, maybe I
Yeah,
forgot. I
okay.
remember.
Don't think of it like that. We just move, like we just so in a list, what we do, we just put it in a place where it's not accessible anymore. So it's not part of the
Okay.
list
Yeah,
anymore.
I
So
mean,
yeah,
no, okay.
copying it is the same. Yeah,
Hmm. So 18 comes here, and then we had 2, and then we
we
are
delete
removing
that
the
node.
2.
Yeah, we delete that node exactly. Yeah, yeah.
Okay.
Okay. So now 2 is not here anymore. Now, so we need to rearrange this, right? So this is not a min heap anymore, right? Nomit, how do we change
Yes.
this?
We'll take the smaller of the children and then promote it to the parent.
Yeah, since this is the min heap, so we take the smaller of the children and promote it up. So 18 comes here, right? Still, we have some. I mean, still 18 is not, uh, you know, smaller than both. So 18 comes here and 8 goes here. All right.
Hmm.
So at the end, how will it look like? 6. Tell me.
6 and then 8,
Very good.
18,
Very good.
10.
The rest are the same, right?
Yeah.
25, and we have like 12, and then 15, and then 20. Okay. Now they are saying that we are going to insert 5. Okay. So now we are inserting 5. Okay. So now 5 is the minimum most element here, right? So,
Hmm.
so after inserting 5, what do you do? What do you know? What do we do?
They keep promote 5 to the parent.
Correct. So we interchange these, right? So now 5 will again get promoted like this. This again get promoted. So can you help me draw the graph? Let's draw it. Tell me what's first. 5.
5.
Am I right?
Yeah.
Okay. On the left.
6, 8,
So 8 came here. And on the right of 8 it's
10.
going to be very good. So we have 25 on the left, right? So do we have anything else? So I can directly. Okay, we have something on the right of. What is it? What is it? 18. So where is the 18 going to go? 18 is going to go on the right of 6. But you're following me or not?
Yeah.
Okay. Yeah. So this is 12 again. Hey, is everyone able to follow this? Mahi? Uma?
Yeah, yeah.
This is an easy question, right? So yeah, tell me, Mohit. Nomit. So now we have all these things, right? And let's write the, what is it? Heap for this. So how will it tell me? 5.
6, 12, 8,
Mm-hmm.
18, 5, 15, 20, 25,
Hey,
10.
wait, 8, 15. So
8,
8,
8,
18.
8, 18, 15, 20, 25, 10. Level by level.
15. Yeah, 20, 25, 10. Okay, let's check that. 5, 6, 12, 8, 18, 15, 20, 25, 10. Yeah, you got the correct answer. Okay,
Thanks.
great, nice. So hope everyone is clear with that, right, guys?
Yeah.
Great. Okay, so we'll go to the next question. So that is what has happened. Mahi, okay, right? Everyone? Fine. Oma, can you take this question?
Yeah.
I don't think I need to copy this. Go ahead.
Yeah, suppose we have a min heap H which contains n elements and is implemented using a list. We want to update the value located at index I. What will be the complexity of the worst case of an efficient algorithm to perform this update operation? So,
Hmm.
what is height represent? It's a height, right?
Yeah, height of the heap. That's right.
Yeah, which contains n elements.
Okay. Containing n elements is implemented using a list. We want to update the value located at the index I. Okay, let's say like we have some it's a min heap, right? Minimum value should be at the top, so it's fine. Like I can write it like this. This is still a min heap, right, Uma?
Yeah.
Okay. So and it is having n elements. So n equal to 7 here in this case. Okay. It's implemented using a list. Okay. So we want to update the value located at index I. So index I is going to be what? Let's say we want to index 6, index 5. Okay. So 0, 1, 2, 3, 4, 5. This is the index 5. Am I right?
Yeah.
Okay. We want to update this. So what will be the complexity of worst case of an efficient algorithm to perform the update operation? Mm-hmm. Tell me.
Gokul, in this example, it's better if you take
Different
the
numbers.
top element to be 2, 3, like let it be 2, 3, 4, 5, 6, and update the fifth index to 1 so that you can see the worst
Okay.
case.
Sure.
Yeah.
Right?
So the worst case will be we will exchange with the swap with the parent and goes up to the root node, right?
Yeah, correct.
Hmm?
So
So let's say we want to update this 7 to 1, right?
yeah, so
Hmm?
we always swap with the parent and then goes up to the node, root node, right?
Is that what happens always? It's for deleting, right? So this is updating we are doing. Is deleting and updating the same? No, I think. So we are updating the value 7 to 1. We are replacing that value or changing the value.
Okay,
Yeah, so
I'm
we
not
have to
getting
compare
what
it to
you're
the parent.
saying.
I think Uma's right. So we compare 1 with 4 and we realize 1 is smaller than 4, right? And when
Correct.
we exchange.
What do you
Yeah,
mean
we do it.
updating? I'm still not getting it. What are we doing at 7?
We're
We are
changing the value at
we are
7.
removing 7 and writing it as 1.
Okay. Then
Okay,
we
now
have to
we have,
compare with parent only, right?
yeah, all the parents.
Yeah.
You're right, Uma. Maybe
So
I got
if
it
we are
wrong.
on the right side, we are going only one way, right?
Yeah,
Yeah, you're
We are
right.
not going to go through all the elements.
So
you
maximum you
don't.
need to
Yeah,
go till this
So
point, right? In the
yeah,
minutes.
so that will be half of it. So it might be log n. That's why I
Not
still
log,
not.
it's ideally log n.
yeah. Heap is always height of log n, so you can
Uh,
just
Okay, so yesterday we were doing the same question. No, that was n. So I got a little confused with that. So that is actually searching the elements. So that is why we got n, right?
Correct. Yeah. So in order to
why you
search an element in a
searching?
binary search, I mean in a heap.
In a heap. Okay.
Okay. So this is only updating. It is only we are doing half. But for searching, we go through everything. I think that is why it was n yesterday in that question.
If you're maintaining a max heap, okay. Even in a max heap, searching for an element, right? Okay. Yeah, maybe.
No, see,
Yeah,
max
you
heap
can't
or
search for
min
an
heap it
element
is
unless
fine.
you go through all elements. Correct. Okay, sorry. I was thinking confusing between binary trees and heaps.
Wait a minute.
Yeah, that
One
you're right.
second. Wait a minute. So we have it here, and so I have like thousand
You
over here.
remember yesterday, Gokul, we were searching for the element which is not present. So that was the worst case. So
Hmm?
we go through every element of the heap.
Yeah,
In that
yeah.
case, it
You have
was
to
the
go
answer of
through.
one.
Correct.
Because that question is similar to closer to this question. That's why.
Yeah.
Okay, yeah, got it.
Is everyone okay with this? Shibin, Mahi, Nomit.
Yes, Gokul.
Good.
Yes, Gokul.
Yeah, nice. Okay. Fine. That was good discussion. So let's go to the next question. This question, can Shibin take it? It's fine if you
While
just try.
inserting the elements,
1 second. Yeah, I'll just put it here.
while
Go ahead. Read the question. Yeah.
yeah, while inserting the elements 50, 80, 20, 60, 10, 45, 65, 30, and 90 in an empty binary search tree, in the sequence shown, the elements at maximum depth are.
Hmm. So for this, shall we try to draw the binary search tree?
Yeah,
Okay. Tell me what will be coming here.
80
Okay. Where will 20 go?
on the other end. Less than,
Good. Go ahead. So I think you know how to do it, right?
yeah,
Okay. So if anyone doesn't know, you can try, or else I'm gonna go first.
can.
45. Just correct me if I'm going wrong anywhere. All right. 60, and then so we have 30 here, and then 90 should be coming over here. Okay. So what is the element which is the maximum depth? We have two elements. That's correct.
Yeah, 30 and 64, correct.
Yeah. Uma, okay? Mahi, okay? Everyone okay?
Yeah.
Nice. If these kinds of questions comes, then obviously everyone will get good score, right? Okay. So we have these things. So I'll just take the answers also. Not a problem, right? We are gonna
We
study,
had
right?
the same in the graded assignment, right? Similar.
Sorry, Uma.
We had the similar one in graded, right?
For this one, maximum depth.
No, the upcoming
Okay,
question.
I don't know. Okay. So if you had the familiar one, why don't you try this?
No, maybe different. I just looked like this.
No. So Kruskal's algorithm, MCST. So what's the thing for doing the Kruskal's algorithm?
Just go with the minimum weight, right?
Yeah, start with the minimum one and disconnect it, right? Basically.
Yeah.
Disjoint set. We use Kruskal algorithm for disjoint sets. So E and A. So first one is going to be 1, right? This is the lowest, right? So then we take the next one. Am I right?
Yeah.
And if we take this edge, it is going to form a cycle.
Yeah.
So we can't take this. We can't take this.
CB we can take it is 3, right?
Yeah. So next we take this, right? So we can't take this. AB also we cannot take because it's forming a cycle, right?
AF we can take.
A, E, C, B, and A will so form the cycle, and then here it is AF, right?
Yeah, that's all I think,
So,
right?
okay, I'll just take the other two options also. Three more options are there. Yep, here we are. Go ahead. Okay, so first one, like AE is there, right? Then AD. In this case, we are not having, but let's go and see. So what is this question about? Like, Uma, can you tell me what is trick in this question?
Yeah, we are going for the possible MST, right?
Mm-hmm.
Because the weights are similar, so we will get more options, I think. Am I right?
Correct.
Yeah.
So let's say that why is this option wrong? Why are these two options wrong?
It must be forming a cycle. I think so.
Okay. So we have
AD,
AE and
CB.
AD. No, next one is second option is AD, right?
Okay, AE, AD,
AE, AD,
BC,
BC.
It's
AB.
wrong there itself, right?
Sorry.
Because it's choosing the edge with weight 3 when you have edges with weight 2.
Okay. So
When
that's
you
the
go to the third option itself, you're wrong.
okay. So they are saying that in which order? In that order, right?
So in option number C,
No, but in
AE
Kruskal there is no
has to
order,
be the
right?
first thing to add, right?
So there is order, Uma. The
Yes.
order is like you choose the lowest one. Next coming are the next smallest one, second smallest one,
Yeah.
right? So second smallest we have AD and DC and EC, right?
Okay.
You can have three permutations of this.
Okay.
See, AD. Uh,
We choose 2. Yeah.
yeah, that's correct. So and the problem is that only you can have only two because anyhow you are taking AE in all the cases, right?
Okay. Yeah.
So one is already fixed. So that means you can only take two of these, right? If you take the third number two also, the third edge with weight two, it will form a cycle, right? So we are supposed to take only two of those. So that's the ideal reason here. So AD
Yeah.
weight is 2 and CD weight is 2, right? And BC is 3.
Yeah.
And this is
The,
okay. A
the
plus
third
4.
option, the option number C is wrong at when you look at BC itself, because
Mhm.
it's choosing an edge with weight 3, whereas you have an edge with weight 2.
So this should come like this.
Not AB. AB is also edge 4. So I think the even like it's wrong because it's not even choosing uh, uh,
Is it the
EC
only
or
reason, or maybe some other reason that edges are not added also, right?
Ideally, this is not the MCST, I think we can say.
yeah,
Okay.
it's not even the MCST. Yeah,
Huh.
Yeah.
but following Kruskals, it cannot choose BC because it has to choose something of weight 2.
Mm-hmm. So AE, we have CD, and then do we have AD here? Yes, we have AD, and then AB, and then comes AF.
That is wrong.
So
Yeah,
again, this is
AB
also
is
not
wrong.
MCST. This
Yeah,
is not
AB is
MCST.
wrong because it's supposed to choose CB. Yeah,
Hmm. Oh, okay.
Yeah, got it.
What about others? Mahi, Nomit, Shibin.
Yes.
Shibin, you want to say something?
No, I'm okay.
Okay, good. So shall we go to the next question? This question also was easy. Fine. Okay, I think this question, who was doing that? Shibina. Like, who was doing that? Uma was doing that, I think. Right? The next question will be for Mahi. Oh my god, we have the Floyd-Warshall algorithm. I even forgot what it is. So is it like all pass shortest path?
yeah.
Am I right?
It's a dynamic programming paradigm.
Okay. Mahi?
Yeah, it's just asking which is true about Floyd-Warshall algorithm.
Mhm.
So, first option is if the shortest path entry SPII is the
Mhm.
resultant matrix is negative, then it represents the graph has a negative weight cycle. Okay.
Okay. What does this mean?
I means it is a loop. Is it a loop? What is it? ISPII?
That's correct. So starting from, you're right. So let's draw some graph. Okay. Or then like this, then like this. Right. So starting from I, if you're coming back to I, okay. And so this is going to form a cycle, negative cycle, right? Uma? So
Yeah, yeah.
1, 2, and if I give -4 here, see. So what it will do is like every iteration, it keeps on going into this, right? So first time itself it will come like -1 or something, like if we have 10 here, like it depends. I'm saying so every time it reduces, right?
Yeah.
So if the resultant matrix is negative, then it represents there is a negative weight cycle in the graph. Correct? So did you understand,
Yeah,
Mahi?
yeah. Got it.
Yeah. If we
No.
have a negative weight, then the resultant, if it is negative, then it will represent a negative weight cycle.
Correct. So what does this SP of I to I mean? So it's like, so starting
Loop.
from I, if you're, yeah, exactly. If you're able to reach I, but with a negative weight. So what does that ideally mean? It means that there is a negative cycle, right? Hmm?
Yeah.
Mahi, okay with that?
Yeah.
Okay. Second question, second option.
The time complexity of Floyd-Warshall is big of V square, where V is the number of vertices in the graph. So why it is
Uh,
wrong?
so
It's
what is
V
the time
cube.
complexity? What is the time complexity? Hmm?
Mhm.
So let's go and explore that.
It's
Don't
n
worry.
cube.
Huh?
No, the time complexity is
N cube.
yeah n cube because you're doing 3 loops, right? So to get SP of 1 is like finding Dijkstra's. No, not Dijkstra's, I guess.
See, look at this.
Yeah, it's like that. Okay, so you're doing n times you're doing Dijkstra. So it's like, yeah, it's a 3 looped algorithm. So
Is that fine, Mahi?
Yeah, it's at three loops.
Huh. So that's why it is like, VQ,
Yeah.
right, in this way. Does anyone want to say something on this? Uma? Shubhan?
No, fine.
Great,
No.
great, great, great. Okay. Fine. So what's the third one? Go ahead, Mahi.
It works correctly if the graph has a negative edge weight but does not have negative weight cycles.
Huh.
So it is correct.
Correct. So if the negative weights are negative age rate can be possible, but if it is having negative weight cycle, then it's not going to give us a proper one. Good, good. Go ahead.
The formula to compute the shortest path from vertex I to j in Floyd-Warshall algorithm is this.
Mm-hmm.
Okay, what's wrong in this?
So
This is not for Floyd-Warshall.
what does this mean here? Like, that's if it's not, I don't know. Like you're saying that it is not for Floyd-Warshall, but what does this mean? So shortest path. Okay, the kth iteration. Okay, so this is like the iteration number. Okay, from 1 to 2, for example. Okay, equal to minimum of in the previous iteration you would have the shortest path, right? Shortest path of 1 to 2. Okay, plus the previous iteration, like k minus 1 means the previous iteration. Okay, and then 1 to 2, and then let's have something called as 3. Okay, 1 2 3 in between, comma, shortest path of the previous iteration, 3 to 1. So look at this.
3 to 2.
J is 2, right? Yeah, sorry for that. Hmm. So one second. Oh my god. Just give me a second. I just take my charger. It will last 1 minute. So what's the answer here? I mean, what's the trouble here? Mahi, you only should answer. Hello?
Yeah, you're audible.
Yeah, Mahi.
Yeah.
Okay. So look at this. So during the first iteration, okay, we are able to see that what's going to happen. Let's say that from 1 to 2, it is 10. Okay, Mahi,
Okay. So 1
1
to
to
2,
2.
1 to
Yeah,
3.
2 is 10. Okay, but the next iteration, you are able to see that from 1 to 3, and then 3 to 2, if you are able to reach like this, so you get the shortest path as 5.
5, yes.
Right. So look at this. So look at ideally look at what is happening here. So 1 to 2, it is 10 plus 1 to 3. What is 1 to 3? It is 2, comma 3 to 2. It is not the case, right? I mean, so it should be ideally like the comma should have come here and the plus should have gone there.
Yeah. That's
Okay.
what's
So
wrong.
exactly. So shortest path in the previous thing from 1 to 2, wherever you wanted to go. Okay, shortest path of 1 to 2 from in the previous iteration, comma, shortest path of the same thing from 1 to 3, then coming from 3 to 2. Got the point?
Yeah.
So, and then you're taking the minimum of this. Hope you understand this clear, right?
Yeah.
Plus in
That's the
between.
point. Sorry?
Yeah, just put a plus in between the.
Yeah. That's right. That's right. Plus SPK minus 1 order.
Yeah.
Hope it's clear, right? Uma?
Yeah, good. Yesterday we saw this formula. So
Yes, exactly. Yeah, Shibin, you want to say something?
Nothing. Yeah, we are good.
Okay, great. Hi, Nikhil. Just saw you joining. Okay. This is interesting. So, coming to this, guys. Okay. Nikhil, are you here?
You want to zoom out and take a bigger screenshot?
No, it's fine. It's fine. So, if I zoom out, people will be like, it won't be visible for others. Yeah. Okay. Nikhil, can you do this? Are you here? Can you respond?
No, we'll put on
Okay.
the message. I don't think he can. He doesn't have a mic.
So who else is going to do this question now? Who is supposed to do this after Mahi? It's Nomita.
Yeah,
Nomit?
no, I'm not sure whether I can.
Okay. So Shibin, can you try this?
I am not sure about this.
Okay. Okay. So let's see. Let's see. How do you do this question here?
I think, shall I, Gopal? We have to
Yeah.
check
Go ahead.
whether the 2 digit is coming as a prefix. Then we can't get the Huffman code correctly, right?
Yeah.
That is the
That's
only
right.
clue as of now. I checked it. So,
Okay.
like in D, the first option, D01, the same prefix is coming. It is coming as a prefix in C. Then it
Yeah.
will go wrong, right?
Correct. So now what you're saying is that so we can take the smallest. I mean the smallest bit numbers first, right? We have
For
11
the prefix, yeah.
and check for the prefix of the other things. So we have 10 here. So there is no prefix for, but it's not a prefix, right?
Yeah, that won't affect it. But
That
this
won't have it. Correct.
prefix, it will be wrong. Yeah.
Yeah, but 0 1 and this 0 1 can be like divided into this,
Yeah,
right?
so it will be encoded wrongly, right? So
Correct.
DD, it could be encoded as DD
Yeah, yeah.
instead of
So
C.
this can be like DD. You're right.
Yeah.
Is that okay, Shibin?
Yes, yes, I
I
understood.
think it's better if we can draw the graph, right? So then you'll know how to solve the question no matter what. Like instead of trial and error, it's better to draw the graph. So you know that we know that in Huffman coding, the leaves, the letter encoding has to be in the leaves, right?
Correct.
Um, if it's there in between, that means it's a prefix code, right? Because it's not, it violates the prefix code
Huh.
um, property.
So let's do this now. What do you say? So we start from here, and then for F it is 1 1. Correct? 1 1, and we put F over here. Am I right?
Yeah.
Okay. So for 1 0 1 0, it is E. Right? So then we have 0 1, 0 on the left, 1 on the right, and we have D here. Okay. And then for C it is 0 0 1 1. So I'm not gonna put the points. Okay, I'll just directly write this so it will be use less time. So then we have
No,
1.
C0101, no? Which one you're taking?
That's okay. This one I was looking at this option.
Oh, okay. Okay.
I'm drawing for B option.
Okay.
Yeah. So these three things are same. Yeah. So for B it is 0 0 1 0. So we have B here. So and then for 000 we have A here. So this seems like a valid Huffman code. So why is this option wrong? So shall we try to draw the graph for A option and C, or let's try to draw for C option? Which one shall we do? Hello.
C option.
Okay. So
You
we'll
can do
try
it
to
for
draw
C,
it.
but A is very similar to this graph you already drawn. So maybe you can just show a quick example with A also.
Okay. Only one is difference, right?
Yeah, only
Only
one is
C.
different.
Only C is different from A.
Yeah,
Okay.
yeah.
So fine. So what is happening? 0 1, and then it's saying like 0 on the left and 1 on the right. All right. So I'm just
Yeah.
interchanging. I'm just changing this part. Whatever we are drawn.
Which
Yeah.
one you're
Yeah.
drawing?
Sorry, Uma.
Which one you are drawing?
I'm drawing the first option.
Okay.
So only change is this part, right? The C is the only change we have. Uma?
Yeah, yeah.
So 0 1, 0 on the left and 1 on the right. Okay, so now we have C over here. So this clearly says that like there is a condition that the children should be like, there should be a sibling. Either two children or no children, right?